Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Colding, and I'll be your host for today's presentation on the integration of Ansys EMC Plus, SIwave, and HFSS. To submit any questions you have during this webinar, please use the Teams webinar Q&A feature at the top center of the Teams menu bar. After the presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar today, we will address them over email. It is my pleasure to introduce today's speaker, Giuliano Maloney, Principal Product Manager at Ansys, part of Synopsys. Giuliano brings over 25 years of experience in computational electromagnetics with a career that spans both industry and academia. He joined Ansys in 2019 as a product manager for electronic solutions, and since then, he's been instrumental in shaping the direction of advanced tools for EMC, signal integrity, and system-level analysis. He holds a degree in electrical engineering, a master's in semiconductor manufacturing processes, and a PhD focused on automotive EMC and signal integrity. Giuliano is also the author of multiple patents and has published more than 70 technical papers in journals and conferences worldwide. Before joining Ansys, Giuliano held engineering and leadership roles at companies including Motorola, Delphi Automotive Systems, WebTech Wireless, and ESSS, giving him a deep understanding of real-world design challenges and how simulation can solve them. EMA is delighted to have him lead today's session. Without further delay, I give you Giuliano.
Hello, everyone. Thanks, Matt. Thanks, everyone, for joining us today. That was a very nice introduction. I could see a little bit of AI in that, but it was a really good one. Thank you for that. So we have a lot of ground to cover today. We're going to talk about EMC and, of course, how we can integrate different tools with different purpose to solve a systems EMC problem with Ansys EMC Plus. So before I get started, I want to highlight a little bit what is electromagnetic interference. I'm pretty sure most of you in here knows what EMI/EMC is all about, but I really like to show this simulation example that highlights something that people will understand, and then they figure out that EMC and EMI is a complex topic. It's a very important one. Here we have a person holding a driller, right? And we have a TV. And as you can see here in the TV, the image is very noisy, right? And that's because of electromagnetic interference. And then we have basically two mechanisms in here. One is radiated emissions. You can see electromagnetic fields being radiated from that driller, right? And the other one is conducted emissions. So you can see that that driller is also generating some noise that propagates through the cables that goes to the power plug, and that cable, of course, also powers the TV. So you have noise that are being radiated and conducted through the cables, right? Of course, when we're talking about electromagnetic interference, we have a source, a victim, and the coupling path, right? That could be radiated or conducted. I got this slide from a very old friend of mine from Whirlpool in Brazil, and he started his career decades ago designing washing machines. And back at the time, besides the motor, the only electronics component you had in a washing machine was an electromechanical timer. You were switching the timer, and then after some time it was automatically shutting off the washing machine. If you look at today's washing machine, you're gonna see a motor driver switching at the specific frequency, 16 kilohertz. You have microcontrollers, you have Wi-Fi, you have Bluetooth, you have touchscreen display. So you have a lot of more electronics content. And whenever you have something new like a Bluetooth or Wi-Fi antenna, you have to go through a different set of EMC standards in order to certify your product, right? So this is an example of a washing machine, but you can take a look at anything around you. Your computer, your watch, even your bulb, your light bulb. Now you have like light bulb with Zigbee, Wi-Fi. You can control them with a Google or Alexa, right? So when you have more electronics, you're also going to see more signal integrity issues because now you have, more digital signals, you have, faster signals, and also more electromagnetic interference. Now you have more electronics content, in the same amount of space, or usually, smaller spaces, right? Every year you see a phone that is thinner than the other, and you have more connectivity, right? 4G, 5G, millimeter wave. So you have more electronics content in smaller spaces. That increases a lot the chances that you have, electromagnetic interference issues. I've been working with the MIMC for more than 2 decades now, and most of my time I've been working with, in the lab, and more recently with more focus on simulation. And whenever we are seeing someone that are, having some EMI, EMC issues, they explain the workflow that they have in their company. Usually you have someone who knows to design hardware really well. They know all the EMC rules, right? So usually, they create a pre-circuit board with the correct stack up. They make sure, you don't have traces crossing a slot in a reference plane. You don't have signals changing reference planes. Then you build a prototype, you integrate your PCB into your product, you go to the lab, and at that stage, the only thing you can do is pray so you can pass the test, right? And that's a workflow that is valid, and praying is always good. But what if you could pray with confidence, right? What if you could, before you build your first prototype, you investigate and evaluate potential EMC or EMI issues that you might have, so you can predict the EMC behavior of your product, right? And that's what simulation is all about, right? Before you build your first prototype, you can use our tools not only to simulate, but to scan the layout of your PCB. When you hire someone, an EMC expert to look at your PCB, they're going to take a look at the layout, the stack up, right? Why can't we automate that? Yes, we can, and we do that. We have something that's called EMI scanner that's part of SIwave that I'm going to show here, that is basically take the entire PCB and check your layout against those EMC rules, right? But if you look at the EMC, lab tests, especially if you have bigger products like a car in the right-hand side, you're going to need some very expensive equipment, right? The semi-anechoic chamber, and that takes time and money, right? So, whenever you have to go to a lab to certify your product, it's much better if you have lots of confidence, if you have evaluated everything, all the what if scenarios, then you go with confidence and you pass the first time that you go to the lab. You don't want to go and fail, and you have to redesign your product, add some chokes and change cables, connectors, and even worse, redesign the PCB. That can cost a lot of money and time. With the EMI/EMC, you have your product, you go to the lab. With simulation is basically the same thing, right? You have the advantage that you can take a look at things that is very difficult to see in the lab, like electromagnetic fields, right? You can actually see them in a simulation, which is something that can provide you lots of insight where you can improve in your design. But I'm not gonna lie, right? There are many ways to leverage electromagnetic compatibility simulations. Usually, whenever someone fails in the lab, they come and they talk to me. They ask me, hey, can we match, your simulations with the lab results? And I'll say, yeah, but that doesn't solve your problem, right? That's a lot of work. And what you want to do is improve your design so you can pass in the lab, right? Matching results is one thing, but using simulation to improve your design so you don't fail in the lab, that's another thing that is much easier to achieve, and it's much faster. But if you want to replicate exactly what you do in your lab, that's possible. Yes, we have hundreds of companies that are doing this, but it is a process, right? They need to take confidence, in their models. They need to get accurate models from their vendors. They need to understand how simulation works. But if you want to replicate what you have in your lab, yes, we can do it. But it's the equation that you see down below is the integration of SI, signal integrity, power integrity, PCBs, antennas, cables, everything. So it's complex. I'm not going to lie to you, right? Usually you have lots of, users that they design antennas, and that's easy, right? Compared to EMC, I'm not saying that design antenna is easy, but compared to here, you're going to have your antenna as a component as part of your model, right? Signal integrity analysis, you can create a cutout around critical nets in your PCB, you can simulate this, but take a look at here, right? For EMC, usually you have to, simulate your design under test, which is your full PCB with 3D components like connectors, and then you have cables. In this case, we have a bulk current injection probe. So it can be really complex. So it's always that, question, right? Should, we invest a lot of resources to try to replicate something that we do in the lab, or should we just use simulation in order to identify problems before, we go to the lab? And I'm going to show both workflows and how we can leverage these tools in here, SIwave, EMC Plus, and HFSS, to tackle all of these EMC challenges. So I'm going to deep dive now into these three tools. Ansys SIwave is going to be the first tool that I'm going to be talking about. SIwave is a tool that is focused only on print circuit boards and IC packets. So anyone that is designing PCBs, is very familiar with PCB, is going to be very familiar with SIwave. You have concepts like nets, footprint, stack up, layers, that any ECAD engineer is very familiar with. You can run simulations much faster than HFSS or EMC Plus, because SIwave is really focused on those layered structures. So we leverage different numerical techniques in order to achieve faster results. HFSS and EMC Plus, they are 3D tools. You can simulate anything in 3D, so it's going to take more time, right? And it's always going to be more accurate than SIwave. SIwave is what we usually call like 2.5D solver, but it provides extremely accurate results, especially when you hybridize with solvers like HFSS. We also have HFSS, which our flagship tool. I believe most of you are very familiar with. You can solve anything in 3D, from antennas, print circuit boards, more recently ICs, interposers, and radars, many things you can simulate with HFSS. And EMC Plus, which is similar to HFSS, is a 3D full wave solver, but it's really focused on EMC problems, right? So the user interface is really focused on EMC. You have some waveforms for standard, some mil standards, some for radiated immunity, for lightning strikes, for conducted susceptibility. You also have techniques that enables the user to simulate really complex systems, that involves cables with several layers of shielding. It could be braided shield cables, foiled cables and shield cables. And also it provides some, tolerant mesh techniques that handles, really complex geometries really well. So for any EMI-MC problem, Ansys EMC Plus, is the tool to be using to try to solve those problems. Now, what I want to show in here, first I'm going to deep dive and show some details of each one of these tools. But in the end, what I want to show is that usually you have someone in your company that is already using SIwave for PCBs, right? Or someone who's using HFSS for antennas, for example, right? You can take results from SIwave and HFSS and bring them into EMC Plus. So you don't have to start a workflow from scratch, right? You can already take an advantage of established workflows that you already have, likely have in your company, that are using our, Ansys tools, to just expand that capability, going from SI, signal integrity, to full EMC simulations. But let's get started with the Ansys SIwave. SIwave, as I was saying, is really focused on print circuit boards and IC packets, and you can run, many kind of analysis. One of them is DCIR, voltage drop. So you have your VRM, you have your component, let's say FPGA, you have to provide power, right? So we compute voltage drop, we also compute current density, power density, and we also compute temperature with ICE-PAC in the background. So it's what we call an electrothermal workflow. And here we're considering the layout, of your PCB. We're considering, the ohmic losses that you have due to currents, right? You can extract S parameter just like, full wave solver. You can run signal integrity analysis, generate those eye diagrams. You can compute resonant modes, that is extremely important for EMI. You can compute near fields, that's what we use as a source for EMC Plus, and also radiated fields, far fields. You can, simulate radiated immunity, induced voltage from a plane wave, and also electromigration. So one of the most used capability in SIwave is SYZ and RLCG extraction. Basically, you have a design, a print circuit board, or in this case, a package on a PCB, and we extract either S parameters or RLC's, resistance, inductance, and capacitance, a function of frequency, and we generate a model, a circuit model. It could be a touchstone file from S parameters or a SPICE model, from RLC, and we take that model that includes all the electromagnetic behavior of your layout to run a signal integrity analysis, a power electronics analysis, or an EMI/EMC analysis. We also have some really focused EMI capabilities in SIwave. And I was saying, the first one is an EMI scanner. EMI scanner is basically the same thing as you do when you hire someone to look at the layout of your PCB to try to identify potential flaws, right? Here in this case, you see on the left-hand side, some of these rules. So when you have a signal reference crossing a split, changing reference planes, or if you have two traces that are really close to each other, you might have crosstalk. We identify all of these issues from your layout. We're not running any simulations in here. We're just looking at your layout, just like an EMC expert will do, right? And we can go one step further. We have a tool that's called EMI Explorer. That's the next step from EMI Scanner. We actually see those flaws and we provide some feedback and say, hey, you might want to use this capacitor in here, to be used as a current path return, for this high frequency signal. And then we show how much gain or what's the delta it's going to be like, let's say for radiated emissions, if you place a capacitor at a given distance with a given value. But let me show you a real example, right? Here, I have a differential net that is crossing a slot in the reference plane, right? And the EMI scanner flags that, right? You want to solve the reference plane. You don't want a gap in the reference plane, right? Because that's going to radiate. But sometimes you have that, there's no way you can close that. So what do you do? Well, the EMI Explorer is telling me, hey, you might want to add a capacitor, a stitching capacitor in that reference plane at a given distance with a specific value, right? And here, we're changing the distance and the values, and you can actually see the delta that you can expect if you add this capacitor. But then in SIwave, you can actually simulate those two conditions. So on the right-hand side on the top, you see there's no capacitor. You see the electric field at 1 millimeter away from the PCB is really red on that slot, right? The return path, the current is trying to return to the source and see that slot and say, hey, I need to go to the other side. What's going to happen? And it radiates. When you add those capacitors, the current, in this case, a high frequency current will flow, back to the source, through those capacitors. And you see that you don't have that hotspot of electromagnetic field anymore. We can also look at the impedance and crosstalk. So what happens is that when you're designing your PCB for high-speed serial channels, you either design for, a specific impedance, let's say 50 ohms for single-ended nets or 100 ohms for differential nets. And you have those equations that you can use based on the thickness of your dielectric, the decay, and also the width and the thickness of the traces, right? But is it something that is easy to do like in an entire board? Sometimes, you might just, use the same width from a microstrip to a strip line, from the top layer to an inner layer. And they have to be like different widths, if you're using the same dielectric, right? So with impedance scan, we look at the board, at your entire board, and I'm going to show a video how to do this. It takes just a few seconds. And here, for example, we're seeing that there's an area where it's not 50 ohms. And you can actually see that there's another trace in a different layer, adjacent layer, that is actually, working as a reference. So that changed the impedance, So things like this, we can easily catch just by running those scanners in SIwave that takes like seconds and maybe 2 clicks, sometimes minutes, depends on the complexity of your PCB. And one thing that most people, they don't consider during their design is the temperature effects, right? Sometimes you design a PCB and that PCB goes to the underhood of the vehicle where temperatures are really high. So you have not only thermal noise, you have jitter on your signals, you have different, properties for dielectric, even for your copper, right, your metals. So what we do in SIwave, since we can compute temperature, we can use dynamic model for capacitors. So here, in the middle of the screen, you see one of those dynamic spice models for a specific capacitor, right? So depending on the temperature and the DC bias, you can see that the impedance as a function of frequency changes, right? So that's something that we can take into consideration. And the temperature can also affect our AC solvers, like S parameter extractions, near fields, and far fields. So I'm going to show one example here for this board. That's the one that I'm going to be using in SIwave, where in this particular case, we have 4 memory modules. Only the right-hand side one is actually working. So the temperature is higher on the right-hand side. If you run the impedance scanner, you're going to see like in the middle of the board, a trace that is changing the colors. That's because it's changing impedance, but not because the cross section is changing. It's because the temperature on this board is different from the right side to the left side, and that changed the electromagnetic material properties across the board, right? So that's something that we can take into consideration. Here what you're going to see is an animation showing the velocity of the air. So we have a cooler on the left hand side, and you can actually see now the traces, and you see that trace in the middle that is showing the cross section is the same, the width is the same, right? But the color is changing. That means the impedance is changing, and that's based on the temperature and not the geometry, the layout, or the stack up itself. So that's something that we can consider, and we're seeing more and more, users that are considering this because they design, everything seems to be fine, even in simulations. But when they take to the real world, they put a PCB where they're supposed to be, those things happen. So let's take a look at this board in 2 different, environments. On the top one, you have a forced convection. So you have a cooler, a fan, from the right top hand side. So that's the reason, you see blue and then green and then red, right? Because blue is closer to the fan, so its temperature is lower. And on the bottom is natural convection. So all the, all the memory models, they have, basically the same temperature. If you extract S parameters, you're going to see insertion loss. There's some switching, on the response, and that's because of the temperature effects on the material properties. And if you run a signal integrity analysis where your drivers can also take advantage of that temperature information, you're going to see when you have a natural convection, you have a much closer eye when you have a forced convection. So you can take advantage of those electrothermal simulations, for signal integrity and EMC simulations. So usually SIwave is widely used for signal integrity simulations, right? People, they extract S parameters, compute temperature, they generate those eye diagrams, but they can, with the click of a button, generate those near fields using that data, right? And that near field can be used into EMC Plus as a source, and that's what I'm going to show later. So let's switch gear and talk a little bit about HFSS. HFSS is widely used. It stands for High Frequency Structure Simulator. So we also use HFSS for SIPI, Signal Integrity, Power Integrity. Is not as fast as SIwave, but it's a 3D full wave simulation. It's extremely accurate, but also for RF and microwave, antenna design, antenna placement, radar cross-section, and biomedical applications. I mean, we have thousands of HFSS users. Thousands of companies actually are using HFSS. And it has been on the market, for more than 4 decades. So it's a very established tool. And the reason HFSS is the leader in the high frequency electromagnetic simulation market is because of the accuracy, right? Usually, most of the tools, including other physics, the user needs to provide what you're seeing here. We call the mesh in order to solve, equations. In our case, Maxwell equations. HFSS, requires only the geometry and the material properties, which we already have in the library, and we automatically generate that mesh for you. We call that adaptive mesh refinement. With that, we provide a more the most accurate mesh possible and most efficiently. Because you see here, we have larger elements where the electromagnetic field gradient is not as strong, right? And we have smaller elements, those smaller tetrahedra closer to those patch antennas and the feed network, because the electromagnetic field changes varies a lot in that region. So that's the reason HFSS is widely used. And we have many different solvers, right? We have finite elements in the frequency and time domain. We have the method of moments, which is a surface-based, solver. We can hybridize those using what we call PHEBE, finite element boundary integral. We have SBR plus, asymptotic techniques, shooting bounce array techniques with advanced diffractions, like creeping waves and UTD, uniform theory of diffraction. And we can hybridize everything using what we call DDM, domain decomposition method. But it's a different story, right? The reason I'm bringing HFSS in here is because HFSS uses, or we have this capability, we have a patent in this, we have introduced it to the market, the concept that called encrypted 3D components. So what happens is what you're seeing here is a PCB is made of 3D components, right? You have connectors and then you have cables, capacitors. And the problem that we always had, or we saw in the industry, is that someone who is designing a PCB, they're not designing the connector. They're buying the connector from someone, right? And that vendor, they don't want to supply the connector because it's their IP, right? So they don't want to supply the HFSS model. So what we came up with was the idea of encrypted 3D components. So, the vendors, they can encrypt those components like a connector, so they can hide material properties, they can hide geometries, and they even can hide the fields inside of these components. But someone who's designing a PCB can actually take that component and put it in there in the PCB and evaluate, signal integrity and even radiated fields. You can't see the fields inside, but you can see fields outside. And we have many hundreds of companies that are using this workflow. We already shipping, we include some 3D encrypted models. Here's just some examples. We have lots of for EMI/EMC. We have bulk current injections. We have some of the antennas. We even have some, test bench models like CISPR 25 for automotive EMC standards. But we have here like example, like a choke from Worth, right? You can just bring that, you see the part number in here, and put that on your PCB. You're not going to be able to see the material properties of the core or see the fields inside, but you're going to be able to see the fields outside, what's being radiated from this choke, and how is that choke suppressing the noise in your product. But you see here, we have many other components everywhere. Here's one example on the right-hand side of the encrypted HDMI connector. So on the most left-hand side, it's unencrypted, so you can see everything. But then you have the encrypted component. Basically, we can create a box and say, hey, I don't want to show anything that is inside this box. Even though HFSS knows what's inside that box, the user can't see what's inside. And that's extremely important, right? Especially if you have like 3D, chip antennas. Like in the middle of the screen, you have some digital traces, and you have a Wi-Fi antenna, like those ceramic chip antennas. And if you wanted to account, for the coupling between the traces and the antenna, you need, the geometry of that antenna. And here you can see the Wi-Fi spectrum when they turn on and off that differential clock. You see the interference in that. Actually, this is what we call desense. The digital signals are desensing the radius of the antenna. One very interesting application that it's already being used by many companies, and you can actually see at the FCC website, is for 5G millimeter wave on some electronics devices. So with 5G millimeter wave, instead of having one antenna, you have an antenna array. And that's the animation you're seeing here. The reason we have an array is that because you can change the excitation of each individual antenna, magnitude and phase, and you can actually focus the radiation pattern, into the user. Usually we have those antennas that radiates equally, all directions, at least on one plane, like horizontal plane, isotropic antennas. But that's not a very good usage of the electromagnetic energy, right? If you can focus on the user, like what you're seeing here, you can improve the communication channel. And that 5G millimeter wave works at 28 gigahertz. It's very high frequency, right? For EMC, we're used to, lower frequencies. And instead of having radiated emissions, what we measure at that frequency is what we call power density, at a very specific distance from, in this case, the cell phone, right? And if you go to the FCC website, here's just some very old examples and links. You can actually click on that link and, for example, Samsung Galaxy S20. It's going to open the report that you're going to see on the right hand side. You're going to see like HFSS mesh. You're going to see some measurements and simulation results that are matching really well. But you might be asking, well, if they have measurements, why are they simulating? Remember that radiation pattern, that can go anywhere. You don't want to measure all the possible combinations at 28 gigahertz. That's going to take forever, right? So, companies, they augment the FCC report with simulation once they have this kind of match. But then there's another question. All of these products in here, and there are, hundreds of more, LG, Motorola, Netgear, Samsung, they don't design the 5G modules, right? They design their product. So how come they can actually get this and simulate the entire system? Because of encrypted 3D components. Someone else is designing the 5G module and they're providing the 5G module as an encrypted component to all of these companies so they can simulate everything as you can see in here. So this is the test, those are reports that you can click there open, right? You're going to be able to see this, those 3D components in the works and how it's being used by the industry so far. And you can take, those 3D components encrypted, get the fields around it and use EMC Plus. And that's the workflow that I'm going to show. But before we get to that, let me give you guys an overview of Ansys EMC Plus. So Ansys EMC Plus is just like HFSS, the 3D full wave solver. You can simulate basically anything in 3D. It's really focused on electromagnetic compatibility applications. It's been developed by EMA. They have almost half a century, almost 50 years in experience on EMC, not only developing the code itself, but also providing, technical consulting services. So you're going to see some really, remarkable, comparison between simulation and measurements from EMC Plus. So they started with aerospace and defense. So all of these really expensive testing like HERF, high intensity radiated fields, or lightning, that's what they started with, electromagnetic pulse. But then, we have, hundreds of companies now using EMC Plus in other industries like automotive, high tech, biomedical, and more recently, even in the semiconductor space. So here's some of the EMC applications that we can solve with EMC Plus, right? We have HERF, high intensity radiated fields, electromagnetic pulse. So here you have an airplane and then you have an electromagnetic plane wave. You can actually compute the coupling from that plane wave, into cables inside your airplane, right? You can also compute shielding effectiveness. That's what we have in here. So you have probes inside your canopy, and once you have that incident plane wave, you can compute the shielding effectiveness. Lightning transients, right? So you can see here an entire airplane with all the cables, right? You can see the induced current and into those cables, due to a lightning strike. And here I want to emphasize this is a full airplane with all the cables. You're not going to see any other tool in the market that can actually handle this kind of model besides EMC Plus. Cable crosstalk, that's bread and butter, right? They have a multi-conductor transmission line solver to compute, all the RLCs for the cables, and they co-simulate that with the 3D environment. They use a finite difference time domain for 3D. You can also see, radiated fields, radiated emissions from these cables, and of course, conducted susceptibility. This is a bolt current injection example, and there are many other applications, right? Just a handful of applications that we use EMC Plus for. And like I was saying, they have been on the market for many decades, and they have published a lot of, very nice information and comparisons between measurement and simulation. This is one of the Ansys Advantage article. We have a magazine they call Ansys Advantage, where we have lots of cases from customers, and this is a Brazilian aerospace company. I don't think we have too many, so it might be really easy to figure out what, which company we're talking about. And this is actually showing some lightning strikes measurement against simulation. It's on the right hand side. You're going to see lots of dots. Those are measurements measurements, right? And right here you see simulation. So you're going to see a delta, of a specific dB, I think 3 dB, from all of these measurements and the simulation results, right? We have this other one paper with Airbus. They also published this at the Ansys Advantage, but also on some technical conferences, Progress in Electromagnetic Research, where they were evaluating, current density and induced current on cables during a HRF analysis. HRF stands for high intensity radiated fields. Basically, you have an antenna you can see on that picture, and then you have the airplane or just the cabin of the airplane, because having the whole airplane might be a little bit expensive. And you can see on the right hand side, the surface current density and the induced current on those cables, measurement and simulation. You can see that the results, they're matching extremely well, especially for EMC. When we're talking about signal integrity or return loss of an antenna, you're going to see results overlapping, right? But here we're talking about, an airplane with lots of cables with shielding, right? So when you have something like this, that's extremely good. And you might be asking, well, do you have comparisons between EMC Plus and HFSS? Yes. And as long as you have a good mesh for either solvers, they're just solving Maxwell's equation, the results should be virtually the same. So here we have some cables in here, and you see the electric field from EMC Plus and HFSS. They're basically the same. And the fields and the currents, the waveform. We're using two different waveforms. And you can see that, the results are virtually the same. The way that we bring SIwave fields and HFSS fields into EMC Plus is through what we call Huygens current sources. So we have a box around the PCB or around an antenna in HFSS, and we generate equivalent current sources on the surfaces of this box, on the Huygens box, that generates electromagnetic fields external to the box that are the same as you have in the original project. So here on the left-hand side, you see a dipole, and then you have the box around the dipole. You see the fields from HFSS, that's in the frequency domain. And we take the fields on that box, on the Huygens box, we generate current sources, and we bring that into EMA 3D to generate the fields. And you can see that they're virtually the same, right? In EMC Plus, I call here EMA 3D because EMA 3D develops EMC Plus, solves in time domain, but the fields are exactly the same. So let me show you a demo on how to work on these tools and get some of the information. Let's start with SIwave. Imagine that you're a PCB designer, you know PCB really well. So what you can do with SIwave? Well, you can start SIwave and run what I was showing, the impedance scan. So this is SIwave. I can click impedance scan. I want to scan all the nets, 223 nets, right? And I just click launch, right? This simulation took 58 seconds, but you're gonna see if I right click and display all the impedance, you're gonna see the impedance in the entire board, right? So instead of doing those math for all of the cross sections, you can actually get this in less than a minute. And we're solving this, we're not using analytical equations, we're using a math of moment solver. Right, so you can see the impedance is around 50 ohms, mostly everywhere, and you can actually see the couple traces. So the traces in here, the segment of the traces, they have the same color, are actually in the same cross section that we use to solve. So we have thousands of simulations in here that we run like in less than a minute to compute the characteristic impedance of all of these traces, strip lines, microstrip, and we account for all the coupling, right? Trace to planes and so on. So, I know most of the PCB designers, they're calculating, or you have that in the tool already, right? In any EDA tool to specify the width of your trace based on your dielectric, on your stack up, right? But sometimes, you might have some surprises. You might want to scan the entire board, right? Another thing that you can do is simulate crosstalk, right, in frequency and time domain. So that's also really quick simulation. So let me show this 4 nets in here that we're showing. I want to run a crosstalk in time domain. So I'm going to set up one of the traces. So here I have all the 4 nets. In one of the traces, I want to be the aggressor. So I have a driver, 100 picosecond, 1 volt volt. That's my driver voltage, 120 picoseconds. If I click launch, after a few seconds, we're going to have the results, and you're going to see a matrix like this that's going to show the maximum voltage in all of these nets. And if you click them like SA1, you're going to see the near end crosstalk and the far end crosstalk waveform. So you can actually run this for your entire PCB, but then you're going to have to specify the aggressors, right? And you might be asking, how accurate is this? Well, we have many benchmarks, but not too many we can share, right? But this one was one of the IEEE, conferences where we have one of those proposed benchmarks, and we have measurements from the IBM Watson Research Center. And this is actually, we're simulating those traces that you're seeing here, and we're simulating basically the same thing, near end crosstalk and far end crosstalk. So on the left-hand side, you're going to see measurement results, again, for near end and far end. And on the right-hand side, you have simulated results. If we overlay the results on top of each other, you're going to see that they match extremely well. And you can actually see the noise in measurements. That's interesting, right? Something that is difficult to prevent in the lab is actually really easy in simulation, right? You have in the lab, like, you have absorber elements, right? Because you want to absorb electromagnetic waves. You don't want them to reflect, right? In simulation, you have boundary conditions that can actually do this. You have noise in the environment. That's the reason you have an anechoic chamber. But in the simulation, you have vacuum, right? You don't have noise. So those are things that are really interesting to see, and really interesting and important to understand the differences. But let's talk about the bread and butter of SIwave, signal integrity analysis. So we can automate this. We can actually simulate, like, I want to see the eye diagram in all of these nets, A0 to A4. So here's the interesting thing. What I'm going to do here is select the IBIS models. And here's the challenge, right? Simulating 3D and PCB is not a challenge, but getting reliable models for your drivers, that could be a challenge. That's not so much for print circuit board signal integrity. We have IBIS AMI models, but for EMC, sometimes that might be tricky. So you might, have to rely on ideal sources or measurements, right? In this case, what we have here, we have all of these nets, and we have all of the components that are connected. This net is connecting all of these components. And you can set those IBIS models and the waveform. Here's a clock, but I'm going to use a PRBS, so it's a random sequence of bits. I'm not going to use any VRM, but when I hit OK, what SIwave is going to do is create the schematic for me. So it's going to create a circuit netlist with all of the sources connected to those traces in the PCB. So here, what is happening is that you have the PCB in the middle, and then you have all the driver and receivers, IBIS models that you're seeing here, right? And that's created automatically, right? Otherwise, you'd have to extract the S parameter and run those simulations, create that schematic for you manually. But then, we're extracting the S parameter here. They assign the ports automatically, and now we have the results. You have the eye diagram. So this is basically how we run a signal integrity analysis, and we have many companies doing this. Now the next step is more interesting. What if I want to take advantage of these analysis and run an EMC simulation with the fields from these simulation? You can just go and compute near fields, and you can select the frequency range, let's say 30 megahertz to 1 gigahertz. You specify, the number of frequencies, every 1 megahertz, and a box around the PCB, in this case 1 millimeter. And you specify export near field data to AND and FD, and that is what we're going to be using in EMC Plus, right? If you simulate this is going to take a little longer, of course, not a few seconds, because now we're going to simulate near fields using the method moments in here, using grease function. So, we run the simulations. Of course, I'm going to speed up the video, but you can actually see the near fields here in SIwave, right? So you can plot the fields, electric field, magnetic field at any frequency. You can specify transparency. So here's actually, the near fields for every frequency that we're going to bring into EMC Plus, right? but this is SIwave. So with the click of a button, you know, you already have SI simulations. With the click of a button, you can get those near fields and bring into EMC Plus. And you might be asking, hey, how accurate is that? So we have a few examples in here, but I'm just going to show this simple one. We have a trace in here with a clock signal, and the return path, we have a slot. You can't really see this because it's on the reference plane, the ground plane, you know, people call ground plane. But we have measurements for near field simulation for near field and radiated emissions in here. And you're going to see, besides the noise floor, you know, the results are matching extremely well. And this is for SIwave. But again, SIwave is just PCB. Your PCB is going somewhere, right? Inside a case or something. And that's the reason we need EMC Plus. So how can I bring that field into EMC Plus? Well, I have here, you know, EMC Plus. I have my computer case in here. So what I'm going to do is go in here, excitation, near field, and I'm going to select the AND file that was generated from SIwave. When I click open, what you're going to see is that we're bringing the fields in here, and you can just drag and drop, you know, that PCB from SIwave anywhere. Now you might be asking, can I simulate this PCB, everything in 3D, in EMC Plus or even HFSS? Yes, you can, but then it's going to take a lot of time. The whole idea here is that you can just, you know, with a click of a button, take advantage of the signal integrity workflow that you probably have in your company, right? And get those results and bring into EMC Plus. Once you have them here, you know, you place your PCB, you just generate the mesh. You can actually solve and get radiated fields. You can get fields that inducing that are being induced, noise that are being induced in cables because of the fields from that PCB. So here's a, you know, the ease grid for finite difference time domain, and you can just run the simulation. This simulation in here, you know, it took 12 minutes on my laptop, so it doesn't take too long, right? And you can get fields, right? You can generate those animations. You can see radiated fields. They have a very neat way to compute statistic fields anywhere. So instead of having a probe, you can have like a box and they can compute statistics on that. But usually what you're going to see or you want to see is actually the fields at a given distance, right? And that's what you have in here, you know, to try to mimic radiated emissions test that you do in you perform in your lab. So, you know, what you're seeing here is actually a simulation. The fields are propagating because of the SIwave simulation. There's no other source in here. We have a cable in there that is actually capturing those noise that you can see in here, but then you have the radiated fields. Now with the you know, the harmonics from the digital signals from SIwave, but also the resonance from this cavity, right? So that's a very interesting workflow. With a click of a button, you generate SIwave results, and in a few minutes, you set up this model in EMC Plus and run the simulation. Now let's talk about HFSS. You can basically do the same thing. So imagine that I have a Wi-Fi antenna that's bread and butter for HFSS. You see Smith chart, return loss. And here I have a box around that antenna, the Huygens box. I want to have a box that is close to the antenna. So I want to capture the fields in there, the near fields. So here we see the fields in a cross section. You know, what I'm going to do here is actually plot the fields on that box. So I'm going to hide this. I'm going to select the Huygens box, and I'm just going to plot the field so you can actually see the information that we will be bringing into EMC Plus. Right, so these are the fields on the Huygens box. So if you go to view ACT extension, it's going to open this window on the right hand side where you have this HFSS EMA 3D link where you can specify the sweep, the frequency sweep. You can specify the Huygens box that you want, right? And you can just click finish and you're going to generate some files, right? If you go to EMC Plus, this is a different model. Now you go to the same place, import near fields, and now you choose XML files. And once you click in here, XML files, you're going to see the near fields in that Huygens box. That's going to be on the way. It's going to be imported right now. So we're reading the files, and here it goes. So you can actually place the fields where you have that antenna. right? And again, can you simulate the antenna here? Yes, but since you already have that in HFSS, why just not bring the antenna in here and run the simulation? And the best thing is that you're not limited to 1-year field source, right? So here we also have a memory board. So I might want to bring the SIwave simulation here. So you go again to the same place, but instead of XML, you select the AND file. So you bring the PCB fields in here. So just wait a few seconds. Pretty much the same workflow. It's extremely easy. You now have the PCB from SIwave. You just drag and drop to the same place and run the EMC analysis. You can get radiated fields, induced fields and cables, compute, anything you want. So here, we're taking advantage of 2 established workflows that we already have for SIwave, signal integrity, and HFSS antennas, right? So, as usual, EMC engineer, they're responsible for everything, but they don't have to be expert in signal integrity. They don't have to be an expert in antenna, even though that always helps, right? But here, what I'm trying to show is that if you already have SIwave, HFSS, with a click of a button, you can bring that into EMC Plus. And the workflow in here, as you see here, is extremely easy, right? You set up your model and then you run the simulations and you can get the fields like what you're seeing here on the right-hand side. So the key takeaways in here is that, you can take advantage of, different workflows that you might already have in your company for signal integrity, RF applications, using other tools and bring that into EMC Plus. So you can take a look of your entire system, right, with all of these components. So with that, I think we're on time, and I'd like to wrap up my presentation by thanking all of you for your time. And if we have any questions and if we have time, let's go and try to answer some of them. Thank you.
Excellent. Thank you very much for such an informative presentation, Giuliano. Again, I think now we can transition to the Q&A portion of the webinar for the last 10 minutes here. As a reminder, all attendees are encouraged to submit questions to the team's Q&A feature to be answered at this time. So with that, let's begin with some of the questions that we've received. The first one here is, can I use a custom rule set which is beyond the rules listed in the EMI checker?
Yeah, we do have an XML that you can actually change some of the rules, but if it's something that is extremely new, like if you want to compute like overlapping the area that is overlapping a ground and the reference plane, a ground and a power plane, that might need some work on our side. So there's some flexibility, but if it's a rule that is brand new, then you're going to have to ask us to add that to the tool.
Excellent. Thank you. Next question is, for encrypted HFSS components, the field coupling to/from the encrypted geometry with the rest of the setup is bidirectional, not unidirectional like a Huygens box?
With the 3D components, there's no field link. It's the actual geometry is there, but only the solver can see. So there's no field coupling like what we're showing here with the Huygens box. The Huygens box here is one way, right? The SIwave and the HFSS fields, they have, they're radiating to the EMC Plus environment. But the 3D components, the actual model itself. So, if you have a port in there, like an antenna, and it's encrypted, you can actually have external noise and you can actually compute that, the noise induced into that part of that antenna, even though you can't see the antenna, what's inside of material properties. So there's no field coupling on 3D components. It's the actual 3D components, but some of the information are encrypted, depending on the user who created material properties, geometries and objects. So it's the actual geometry that is there.
Okay, great. Next question is, can you use your own waveform, like, for example, a mil spec?
Oh, yes, absolutely. Yeah, you can use your waveform or spectrum. If you have a time domain waveform, like for a mil spec, like for EMP or HERF, you can use it. If you have like a spectrum, measurement from your spectrum analyzer, you can also use that for different type of simulations. But yeah, by no means, we have some of the standards, waveforms We have some sources in circuits that you can create them. You have plane waves where you can provide a plane wave time domain waveform. But if you have waveform from your scope, a table in Excel spreadsheet like time, amplitude, it doesn't matter if it's current, electric field, or current, we can use them. Yeah, there's no limitation. We're very flexible with regards to the input of the simulations.
Awesome. Next question is Ansys EMC Plus part of the Ansys electronics license?
So Ansys Electronics license. Oh, well, we do have Ansys Electronics Enterprise, which includes HFSS, SIwave, Maxwell Q3D, and iSpec. No, so Ansys EMC Plus is a separate license like MotorCAD, like Charge Plus and C-Matrix. Those are not included in Electronics Enterprise. They are considered like a separate product, separate SKU that is not included in Electronics Enterprise.
Thank you. Next question is, how does it work for power supplies with MOSFETs or switches? Will we have to apply the voltages at different nodes in SIwave?
Yeah, that's an interesting question. What we do in this case is what we call a co-simulation, right? We have many DC-DC converters, simulations, and now with electrifications, drivetrains, book converter. So we do what we call a co-simulation. Basically, what we do, you can actually add those spice models for the switching devices in SIwave, but usually what we do, we place ports in there or sinks and sorts, and then we bring that into circuits, right? We even ship some silicon carbide models from ST Microelectronics and Infineon that are widely used in the automotive industry. And we have an example in here. If you go to File Open Examples, Circuits, there's a EMC and there's a power board where we have the SIwave power board and those switching devices. And basically we show that you have in circuits all of your switching devices, your sources. We even have a space vector modulation tool that shows all the three-phase current waveforms for your motor. Basically, we have that example, but we have many more. But basically, what you have to do is co-simulate circuits with the either SIwave or Q3D in this case.
Okay, and the next question is, what are the limitations of student versions of the three products?
Okay, that's an excellent question. There are few limitations for electronics overall. Basically, is the size of the problem. So you can't simulate something like what you're seeing here. Maybe this antenna, if you remove the dielectric, maybe it will work, but definitely not the entire CPU enclosure that you can see here. And some of the capabilities, like SIwave is not included, and HFSS 3D layout is also not included. But other than that, is basically the size of the problem.
Okay, and then another question is, do you have any samples for beginners on how to simulate or design PCBs with basic radios like nRF52 and PCB/chip antennas?
Yes, absolutely. We have some training material, and also we have what we call Ansys Learning Hub, where we do have material for the chip antennas and printed antennas. Actually, in HFSS, even in the student version, if you go to Open File Examples Antennas, you're going to see an encrypted antenna from Molex in a print circuit board with the impedance matching network that you can play with. So it's actually available even in one of the examples that we ship with install.
Excellent. Next question is the mesh in EMA's products, I assume this attendee means EMC Plus, FDTD type of structured mesh, does it have localized refinement?
Correct. So there, find a difference time domain grid, is grid. You can have a subdomain with smaller mesh cells, but it's not, like adaptive mesh refinement like FEM in HFSS. It's an FDTD where you can have regions with smaller mesh, like usually close to the if you want to simulate like a PCB in 3D or closer to models where you have small details, you can create a subdomain with smaller, mesh cells. But you're correct; it's FDTD based use grid.
Okay, and the next question is, if the CAD model doesn't have cables, can you recreate them in EMC Plus, assign cable properties, and run this as part of the simulation?
Oh yeah, absolutely, absolutely. We import KBL files, that already brings all the routing and the cross section of the cables. But basically, what you have to do in EMC Plus, you design a line or one of these tubes, like you're seeing here. You can extract a line from that tube, and you can right-click and specify your cross section. You can add conductors, you can add shielding, and you can, connect the shielding. You can have pigtails, connect the shield to a 3D geometry. It's extremely flexible and easy to create cables in EMC Plus.
Next question is, can you tell us more about how EMC Plus handles dirty or complex geometry? Does it use space claim or discovery model prep toolsets?
That's a great question. So we don't have space claim anymore. It was replaced by Discovery, and EMC Plus, just like Charge Plus, uses the Discovery user interface as the UI. So EMC Plus is in Discovery, right? I was showing here those videos and they're Discovery videos. So you have all the capability that is available for Discovery to improve your CAD. But sometimes that's not really necessary. When you're using a numerical technique like FEM, where you have to mesh all the details, then you have to clean and adapt the geometry. But for EMC Plus, they have a very tolerant mesh, algorithm, just like any FDTD tool, right? You don't have to simplify your CAD model really, thoroughly. But yeah, you have all that capability from Discovery, Legacy Space Claim. It's already built into EMC Plus. It's there.
All right, and we're nearly out of time, so I think we have time for just one more question. And that is there any in-depth Ansys EMC Plus training available on ALH or elsewhere?
Yes, there is. There is one in ALH, and there's lots of tutorials if you go to the help section with video tutorials and step-by-step and models, including the SIwave link. So yeah, it's available. And of course, our team in here at Ansys, the team in EMA, at EMA, we will be extremely happy to provide more information and training material, focused on your specific application.
Excellent. Thank you very much, Giuliano, and thank you to everybody who's
Yeah,
taken the time
thanks.
to listen to today's presentation. It's now time for us to conclude this session. Again, any questions that were submitted to the Teams Q&A feature that we did not address today will be answered via email. And following today's webinar, all registrants will receive an email from us with a link to the recording of this webinar, along with a copy of Giuliano's presentation. If you have any other questions about a particular section of interest to you, please feel free to either respond to that email or reply directly through the ema3d.com website. Up next in the EMA Solving Electromagnetic Challenges series is PCBA Design Decisions and SIEMC Consequences, which will occur on November 19th at 11 a.m. Mountain, 1 p.m. Eastern. Thank you all very much for your time and attention, and I hope you all have a great rest of your day.
Thanks, everyone.